So I'm going to be explaining Hess's law, which is a way of determining how much energy comes out of a chemical reaction. But first, I have to explain this term heat of formation. And heat of formation is the amount of energy that it takes to form 1 mole of a compound from simple elements. It's designated by this delta H with a little f. And it's pretty slick how this whole thing works. Now, enthalpies for elements is always 0. Okay, so it's when you see that delta, it's sort of a change. So we're assuming that the elements have been formed when, the planet congealed from stardust and everything else. But after that, we start making compounds. Well, looking at this equation, I have a carbon, I have an oxygen, which are both in their elemental forms, and it's going to produce CO2. Well, the amount of heat that comes out of that reaction turns out to be negative 395 -395.5 kilojoules of heat. Now, that negative indicates that it's exothermic. So that would give off, so that would be an exothermic reaction. I could have also put that amount of energy incorporated into the product side of the equation. But that's the amount of energy that's going to come out when CO2 is formed. Being a relatively large negative number indicates that CO2 is pretty darn stable, and it is. Now, I can go through this, and people have done this, and they've figured out heats of formation for a whole bunch of compounds. For example, if I was looking at C3H8, I'd go to a table, and I'd see that delta HF, and it's real specific. You got to be careful of the phases that things are in, because a phase change is going to require energy, and that's going to change the heat of formation. So the heat of formation for C3H8 turns out to be a negative 103.8 kilojoules per mole. I could look up another compound, H2O. H2O in the liquid phase, the amount of energy it takes to form that from elements turns out to be minus 285.8. And remember, those negative signs indicate that heat was produced in the creation of those compounds. And then, like I said before, I already figured out, or I'll use the example of CO2. In the gas phase, delta H there of formation was equal to minus 393.5 kilojoules per mole. And you would go to a table and you would find these values, all right, for a given reaction. So here I'm going to show you how this all works, okay? So the reaction that I want to do, and I want to figure out, is going to be C3H8. And if you're a chemical engineer, this is a big deal, that you can figure out how much energy is produced on paper. You don't have to worry about having your factory meltdown and explosions going off. You can do this all on a piece of paper and get a good idea of what's going to happen. So, obviously that's a big deal. So here is a combustion reaction. I have propane plus oxygen. 5 oxygen is going to produce 3 CO2s and H2O. The classic combustion where you produce the products are CO2 and H2O. Now, Hess's law states this: the enthalpy delta H for a reaction is going to equal the sum of the enthalpies of formation, the energy it takes to form those compounds from bonds, of the products minus the sum of the enthalpies of formation of the reactants. Very simple. So, I can figure out how much energy came out of this reaction by doing this. Delta H for this reaction, the enthalpy for this reaction, equals the sum of the products. Well, CO2 was, and I'll just put it back up here, minus 393.5. H2O was minus 285.8. oxygen in its elemental form is 0, and propane was minus 103.8 kilojoules per mole. So, products are always on the right side. Since these heats of formation are based per mole, and I have a coefficient of 3 sitting right there, okay, and a coefficient of 4, kind of start using your science or your chemistry logic on that. The heat of formation of the total products will be 3, because of that 3 right there, times a negative 393.5 plus 4, and that 4 is that 4 right there, times a negative 285.8, and now minus, because I just took care of the two products, now I got to take care of the reactant, minus a negative 103.8. The only trick is making sure that all the signs and everything work correctly. But when I solve that, I'm going to get minus 2219.9 kilojoules of heat coming out of that. So I just figured out how much energy would be produced with that reaction based off of thermodynamic tables. So remember, these values are published. That value there, I would look up C3H8 on a table. I'd look up a negative 393.5 for CO2 in the gas phase, so forth. And when it happens to be an element, it is 0. And O2 is in its elemental form. Now that's one version of Hess's law. I'll show you another way that Hess's law can be calculated using the idea of sort of adding two equations together. This is a good example of really what's going on with energy. Energy cannot be created nor destroyed. The energy that is inherent in a compound is there. Propane, inside that propane molecule, there happens to be negative 103.8 kilojoules of energy. You can kind of think of it that way. And that is a part of propane. That part then we can use to, liberate and figure out how much energy is going to come out of these individual reactions. All right?